Namaskar. I am Dr. Neeraj Upadhyay again with you for explaining next module. Here in this module, we will learn about explanation of low spin and high spin complexes by crystal field theory and determination of crystal field stabilization energy. In the last module, I taught you about the basics of CFT. You learned that central metal is treated as positive point charge or positive point dipole, and ligand were considered as negative charge or negative point dipole. The attraction between metal ion and ligand is purely electrostatic in nature, as in the ionic crystal lattice. Therefore, the electric field involved here were called crystal field, and the theory produced by that way is known as crystal field theory. But the bond energy calculated for a transition metal complex didn't match with the experimental value. Therefore, effect of crystal field on d orbitals of central metal ion was suggested to evaluate, like in the octahedral involvement, degeneracy of 5 d orbitals break in 2 sets of d orbitals, that is T2g, which is framed by dxy, dyz and dzx orbital, and Eg, that is framed by 2 degenerate axially oriented d orbitals, that is dz square and dx square minus y square orbitals. The energy difference between the T2g and Eg orbitals are called crystal field splitting, and overall stability gained due to this crystal field is called crystal field stabilization energy. Concept of low spin and high spin octahedral complexes introduced by valence bond theory was also explained by the theory. In this module, we will learn about the explanation of low spin and high spin octahedral complexes by using crystal field theory and determination of crystal field stabilization energy in both of the cases. So, the learning objective of this module are to be able to apply the crystal field theory on low spin and high spin octahedral complexes and to determine value of crystal field stabilization energy in both the cases, that is in the case of low spin and high spin complexes. In crystal field theory, you got to know that due to ligand field, the degeneracy of 5 d orbitals break and the kind of splitting of d orbitals vary geometry to geometry. So, once the degeneracy of 5 d orbitals break, a genuine question comes into the mind that how above principle and Hund's rule will be applied. For example, in case of D4 system, the configuration may be T2G3 Eg1 or T2G4 Eg0. According to above principle, all the energy levels and sublevels are filled in accordance with increasing energy. So, for minimization of total energy of the atom, filling of electrons in higher sublevel before the lower energy sublevel must not be done. Therefore, 2s sublevel completely fills first, then only electrons can be occupied in the 2p sublevel. In our case, both the degenerate set of orbitals are the part of the same d sublevel. So, what will happen if degeneracy of d orbitals break? How electrons will be occupied? Also, Hund's rule of maximum multiplicity states that in the ground state, electrons in the degenerate orbitals are occupied in a way to generate maximum electron multiplicity. It means for a degenerate set of orbitals, electron pairing is only possible once all the degenerate orbitals are singly filled. So, the question arises here that whether we should consider T2g and Ez as new set of orbitals or validity of both the rules will be done by considering them as a part of d orbitals. In order to answer these questions, we need to go to the basics again. Actually, there are two types of orbitals. Orbitals that are singly filled are called paramagnetic orbitals, and orbitals containing paired electrons are called diamagnetic orbitals. All the paramagnetic orbitals orient themselves in order to support the external magnetic field, shows attraction against external magnetic field. Actually, all the electrons have the task to occupy entire spherical arrangement to atom around the nucleus. So, electrons of degenerate orbitals exchange its position from each other to cover entire spherical arrangement of the atom. When two or more electrons with unidirectional spin exchanges its position, that finally shows no net change in the electronic arrangement of electrons in the atom, stabilizes it, and a small amount of energy is released during the process. This released energy is called exchange energy. And as I told you, this stabilizes the atom. For example, in a p3 arrangement, the exchange of position of the electron can be seen here in the orbital arrangement. The spin of 3 electrons in different orbital is represented here by blue, red and green colors. So, due to this exchange of electron, the released energy is called exchange energy. On the other hand, orbitals having paired electrons do not have any net magnetic moment and opposes all the external fields. So, naturally, all orbitals containing paired electrons increases energy of the system. Also, pairing of electrons in an orbital causes electronic repulsion. So, this pairing is done only in a forced way. Pairing energy is the amount of energy that atom need to provide such orbitals for forcefully pairing up the electrons. The greater the repulsion between the electrons, the greater would be the pairing energy. The background behind the validity of Hund's rule is based on these two energies, that is exchange energy and pairing energy. Let's come to the D4 system in an octahedral system again. There is no doubt in filling the first 3 electrons. Obviously, they will be singly filled in T2G sublevel and make a half-filled like arrangement. Now, the 4th electron may enter into EG set of orbitals, but for that the system needs energy equal to crystal field splitting. Also, 4th electron may occupy an orbital of T2G set, but for that system needs additional amount of energy that equals to the pairing energy P. So, for all such systems, there would be genuine competition between delta O and P. The electrons will be occupied in a system which demand less amount of energy in the case of D4 system. In case of D4 system, if delta O is greater than P, then electron will not be jump to EG level and prefer to pair up an orbital of T2G set. This will generate a low spin complex. Similarly, if delta O is smaller than P, then the system will prefer to occupy one of the EG orbital rather than to pair an orbital of T2G set. This creates formation of a high spin complex. Generalizing the concept, in all the systems having delta O greater than P, electrons pair up in T2G level and form a low spin complex. On the other hand, in the system having delta O is smaller than P, the 5 d orbitals, that is 3 T2G orbitals and 2 EG orbitals, first singly fill and then only pairing may start. So, form high spin complex. The same is summarized in the orbital picture given here. Consider an example of Cr2+, that is a case of D4 system, which is shown in the figure here. It should be remembered that it cost crystal field splitting energy to put an electron into the EG orbital, but at the same time pairing of electrons in T2G orbitals also demand energy. For a given metal ion, P, that is pairing energy, is constant. It does not vary with ligand, but it does depend on the oxidation state of the metal ion. However, delta O varies with ligands. Now, let us find and summarize value of crystal field stabilization energy for the system from D1 to D10 arrangement. Let us consider a dx ion containing T2G P EgQ configuration, in which P is the number of electrons in T2G set and Q is the number of electrons occupied in EG set of orbitals. So, X is equal to P plus Q. Change in energy for T2G P EgQ configuration in terms of delta O is equal to loss of energy due to P electrons in T2G set plus gain in energy due to q electrons in Eg set, that is equal to minus 0.4p plus 0.6 q delta O. In this equation, we have not considered pairing energy of the dx ion. Two terms contribute to the pairing energy, that is loss in the exchange energy which occurs upon pairing of electrons and Coulombic repulsion between spin paired electrons. If the pairing energy of the ion is also involved, then the CFSE of the ion is given by the expression CFSE is equal to minus 0.4p plus 0.6 q delta O plus m into p. Now, since delta O is also known as 10 dq, so the equation will become minus 4p plus 6q dq plus mp. Here m represent total number of electron pairs originated due to splitting of orbitals and p is equal to mean pairing energy. Equations 3 and 4 have been used to calculate the CFSE values in terms of delta O and dq respectively. It has been found that under the influence of certain ligands known as weaker ligand, the energy difference between Eg and T2g set of orbitals is relatively small. Hence, the electrons of all the 5d orbitals of these two sets may be supposed to be distributed in Eg and T2g set of orbitals according to Hund's rule, which states that electrons will pair up only when each of the 5d orbitals are at least singly filled. Thus, in the crystal field of weaker ligands, the first three orbitals enter the T2g level, fourth and fifth electrons go to the Eg level, sixth, seventh, eighth electrons occupy the T2g level, and the last two electrons, that is ninth and 10th, go to the Eg set. The octahedral complexes containing weaker ligand are called the weak filled or high spin complexes. The filling of electrons in d orbitals and calculation of CFSE values of high spin or weak filled octahedral complexes can be determined by using the formula CFSE is equal to minus 0.4p plus 0.6 q delta O plus mp, that is equal to minus 4p plus 6q dq plus mp, where m is the difference of paired electrons between split and unsplit state of d orbitals. The value of CFSE from d0 to d10 arrangement is shown here. In case of d1, the single electron is occupied in T2g set, stabilizes the system by minus 0.4 delta O. In case of d2 system, the two electrons are occupied in T2g that stabilizes the system by minus 0.8 delta O. For d3 arrangement in the weak field environment, 3 electrons are occupied by T2g orbitals that stabilize the system by minus 1.2 delta O. In case of d4 arrangement, 3 electrons are occupied in T2g set that stabilizes the system by minus 0.4 into 3 equal to minus 1.2 delta O, and the fourth electron, which get its occupancy in Eg set of orbital, destabilizes the system by plus 0.6 delta O. As a whole, CFSE value will be minus 1.2 delta O plus 0.6 delta O, that will become minus 0.6 delta O. In case of d5 arrangement of the configuration in weak field arrangement would be T2g3 Eg2, each electron of T2g set is stabilized by minus 0.4 delta O, while every electron of Eg set is destabilized by plus 0.6 delta O. As a whole, CFSE would become 0. That is, in case of d5 arrangement in weak field geometry, there is no change in energy of the system in octahedral weak field complexes, just because of symmetrical filling of electrons in 5d orbitals. Similarly, same type of calculation can be done for all other configurations, and the same is summarized in the table shown in your screen. You can see CFSE is either 0 or a negative value. This means in each and every case, molecule in octahedral geometry either give more stability or at least equal stability with respect to the spherical arrangement of 6 ligands, and this is why molecules orient themselves in an octahedral arrangement rather than a spherical arrangement. I have a question for you. In the D10 arrangement, there are 5 pairs of electrons and no energy generated from splitting of d orbitals. So, does octahedral arrangement of D10 destabilize the molecule? Think. I'll come back within a moment. For answering the question, again I would say you have to visualize the entire picture. Atoms in the D10 arrangement itself have 5 paired electrons, and therefore at barycenter atom or ion itself contain plus 5 energy. So, comparing energy of octahedral arrangement with a spherical arrangement, it is found that octahedral molecule is neither stabilized nor destabilized. In octahedral complexes containing stronger ligands, the distribution of d electrons in T2g and Eg orbitals does not obey Hund's rule. The first 6 electrons go to the T2g orbitals and the remaining 4 electrons enter Eg orbitals. The octahedral complexes having stronger ligands are called as low spin or strong field complexes. There would be no change in CFSE value from D1 to D3 and then from D8 to D10 configuration when you compare the CFSE value of low spin and high spin complexes, except value of delta O is higher in low spin or strong field complexes compared to a high spin or weak field arrangement. In D4 arrangement, the 4th electron enters in T2g level as crystal field splitting here is larger than the pairing energy. So, the 4th electrons get occupied in the T2g set of orbitals, which stabilizes the system by 4 into minus 0.4 delta O, that is equal to minus 1.6 delta O. So, the 4th electrons here get paired in the split state of d orbitals, while there were no paired electrons in unsplit state of d orbitals. So, an energy plus P has to be provided to the system for forcefully pairing the electrons in T2g level. As a result, CFSE will become minus 1.6 delta O plus P. Similarly, in the D6 arrangement, 6 electrons are occupied by T2g set of orbitals, giving a stability by the release of energy that is equal to 6 into minus 0.4 delta O equal to minus 2.4 delta O. At the same time, in this configuration, there are 3 pair of electrons in T2g level, which is higher by 2 pair compared to the electronic filling in unsplit state of d orbitals. As a result, total energy of the system would become minus 2.4 delta O plus 2p. Similarly, you can determine energy of all the configuration from D1 to D10 in strong field or low spin arrangement. The filling of electrons in d orbitals and calculation of CFSE value for low spin or strong field octahedral complexes is summarized here in the table. Regarding the filling of electrons, following points may be noted. By comparing the two tables, that is table 1 and table 2, the following conclusion can be established. Whether ligand is strong or weak for D1, D2, D3, D8, D9 and D10 configuration, the arrangement of electrons remains the same. For each of D4, D5, D6 and D7 configuration, there is difference in the arrangement of electrons in low spin and high spin. In all these cases, low spin complexes is having more CFSE and therefore get more stability. The formation of low spin and high spin complexes is decided by comparing magnitude of delta O and P. The magnitude of pairing energy of a certain metal atom or ion remains same in its splitted and unsplitted form. It is therefore only value of delta O decides whether the formed complex will be low spin or high spin. So a genuine question come into mind that can we chalk out the factors that can affect magnitude of crystal field splitting, which in turn can help in expecting formation of low spin or high spin complex. This you will learn in the next module. Like valence bond theory, crystal field theory also supports formation of low spin and high spin complexes. According to crystal field theory, the degeneracy of 5d orbitals break with different arrangements of ligand. In octahedral geometry, 5d orbitals break into set of 3 orbitals called T2g and set of 2 orbitals called EG orbitals. The energy difference between the two levels are called crystal field splitting. If the 5d orbitals feel first unidirectional, by its spin, exchange energy which stabilizes atom or molecule becomes maximum. But to fill the fourth electron in the AG level, the system needs to provide an additional amount of energy equal to its crystal field splitting. And if fourth electron pair up with an electron of T2g orbital, an energy equal to its pairing energy is needed to be supplied to overcome the repulsive forces between electrons in the orbital. Formation of low spin and high spin complex is a result of competition between crystal field splitting and pairing energy. If delta O is greater than P, low spin complex will result and vice versa. The calculation of CFSE indicates that whether the ligand is strong or weak for D1, D2, D3, D8, D9 and D10 configuration, the arrangement of electrons remain the same. For each of D4, D5, D6 and D7 configuration, there is difference in the arrangement of electrons in low spin and high spin arrangement. In all these cases, low spin complexes is having more CFSE value and therefore get more stability. The magnitude of pairing energy of a certain metal atom or ion remains same in its split and unsplit form. It is therefore only value of delta O decides whether the formed complexes will be low spin or high spin. In the next module, we will learn about the factors that affect crystal field stabilization energy. Thank you very much for listening me.